Hello student, this is our compulsory theory course, Physics of Semiconductor Devices, and from this module 1, Properties of Semiconductor, and today we are going to take topic that is a carrier transport phenomenon. Today's lecture will cover the following topic because last lecture we already covered about the extrinsic semiconductor carrier densities, which is for the electrons and holes, and few numericals we solved on already on that. Then in this today lecture in carrier transport phenomenon, in which when in semiconductor material, that is in pure semiconductor, that is intrinsic semiconductor, or extrinsic semiconductor, that is n-type semiconductor and p-type semiconductor, when the carriers are moving, is that maybe electrons or holes, that is how their mobility is there, then how the resistivity or conductivity of them, then we find out how which type of semiconductor is there based on charge carriers by using Hall effect. Then we will also go for the diffusion process. Then we have Einstein's relation between the coefficient of diffusion and charge carriers, then current density equation, and also we'll go for some numericals which is based on this topic. Then what is the mobility? Because already we gone through the what is the carrier density or carrier charge density, which is for intrinsic semiconductor and extrinsic semiconductor. We know that in under thermal equilibrium condition, the average thermal energy of conduction electrons can be obtained from the theorem of equipartition theorem. When electron go from valence band to the conduction band, then that average thermal energy, that is 1/2 of kd. Then we can obtain in terms of electrons semiconductor, which is having like a 3 degrees of freedom. Then we can write the which is in three dimensional space. Then kinetic energy equation we can write, just write, we know that kinetic energy is equal to 1/2 of mv square, and that 1/2 of mv square is equal to 3/2 kT, which is in 3-dimensional place. Then mn is the mass of electron, vth is the thermal velocity, k is a Boltzmann constant, and T, which is temperature. Then the electron semiconductor which move inside your semiconductor when we apply the any condition. For example, here we apply the thermal condition for that, and this thermal motion of an individual electron which visualize inside the semiconductor, because when they are moving inside the semiconductor, they are moving their random motion, and this random scattering from collision, when it moving in semiconductor material, then these electrons will be collide with, or collision will take place between the different atoms. For example, they are colliding with the lattice atoms, then impurity atoms, and other scattering centers. Here is impurity atoms, means if you have extrinsic semiconductor, then your impurities are there, that is your accepted impurity or donor impurity is there. Then during this collision taking place between electrons and the lattice atoms or impurities atoms or other any scattering center, whatever this electron which average distance between collision between them is called as the mean free path, because this phenomenon you studied in thermodynamics, and the average time between the collision between these electrons and lattice atom or with the impurities atom, that is called as the mean free time. And for example, now if we have a situation when we apply some external electric field to the semiconductor material, then how we experience the force, that is F is equal to QE, and that moving with the velocity, that is we call as the drift velocity. See here is schematic is showing very clearly when electron moving in a semiconductor, if we have a random thermal motion, that is without electric field it can move randomly, that is given E is equal to 0, there is no electric field. But when we apply the electric field, due to the random thermal motion of electron, it is become somewhat a specific direction of they moving, and then we can write this equation, because electric field applied, then we can write that is the force F is equal to kV, because apply electron during this free flight between the collision, that momentum gained by electron in the same period, and then momentum is equal to, we know that momentum is equal to P is equal to mv, and then we equate equation F is equal to F is equal to QE, that is nothing but minus QE applied. The moment of applied electron is equal to minus QE tau of C. Q is the charge of electron, E is electric field, tau of C is a mean free time, is equal to mn mass of electron and the velocity of electron. Then this equation we can write, rearrange the term, we can write in terms of velocity, Vn is equal to minus in bracket q tau of c divided by mn into E, and this equation we can write in a quantity, new quantity, that is called as the mobility, and that mu n represent the mobility of electron is equal to q tau of c mn. Then we can write this equation also in terms of mobility equation. You can also write in terms of drift velocity, and the Vp is the drift velocity for the hole is equal to mu p into E, where mu p is the mobility of holes and mu n is equal to minus mu Vn is equal to minus mu n into E. Vn is the drift velocity is equal to minus, because electrons carry the negative charge, and that is a mu n. Mu n is the your mobility of electrons into applied electric field. Then this equation is very important. ABC, drift velocity which is directly proportional to the applied electric field, mobility which is the constant for the material. Then this proportionality is called as the mobility, and this mobility is very important parameter for carrier transport, especially that is electrons and holes which carrier transport inside the semiconductor material, and actually it's showing how strongly the motion of electron is influenced by the applied field. And due to this mobility, when we apply the electric field, how this electron will moving strongly inside the material, the mobility describes it. And then this mobility is related directly to the mean free time between the collisions. Mean free time between collision with whom? Collision with your electron which is moving inside and lattice atom, as well as impurity atoms and your scattering centers. And based of that, that you have two important mechanism which is taking place, that is called, one is lattice scattering and second one is impurity scattering. From that, first one, if you see the lattice scattering, you know, there is a thermal vibration. When we apply the thermal energy to the semiconductor material, the thermal vibration of lattice atom at any temperature which is absolute zero, then due to this thermal vibration of electron, lattice periodic potential and allow energy transfer between carriers. And since here, due to this lattice vibration increases with increasing temperature, and then lattice scatterings become very important for high temperature, and hence the mobility of decreases with increasing temperature, because your electrons will collide with your lattice atom, and it's showing by symbol mu of L, and it decreases proportional T raised to -3/2. Now another important, that is impurity scattering, and this impurity scattering nothing but if you have a donor and acceptor, that is in n-type or in p-type semiconductor, if the ionized open impurity, then the charge carrier with will deflected due to the Coulomb force between them. And this probability is that impurity scattering depends on here total concentration of ionized impurity, that may be donor impurity or acceptor impurity, and then some of this concentration of negatively and positively charged ions. But in lattice scattering, impurity scattering becomes less significant for the which is at the higher temperature. Means here that at higher temperature the carriers are moving faster. The electron is one carrying semiconductor which is moving very faster, as electrons having a lesser mass, but the holes which is having somewhat more effective mass, they move slowly as compared to the electron. Then here the impurity atoms are lattice atom which plays important role when they collide with your collide with the electrons when I apply the electric field. Then we can write this equation. Then here we can write in terms of a tau of C, that is a mean free time. 1 upon tau of C is equal to 1 upon tau C of the lattice atom and 1 upon tau C of the impurity atom. And this is we can write just in terms of your mobility. 1 upon mu is equal to 1 upon mu, or due to the lattice scattering and due to the impurity scattering. And here is important fact we are getting from this figure. If you see, here showing that the mobility electron mobility on y-axis which is showing electron mobility, x-axis which is showing how it is a function of a temperature, how it is a varies with the temperature. This is we just take example of a silicon in which we have a donor concentration, means like n behaves like n type semiconductor. How does the mobility behaves with the temperature? If you see the temperature from 100 degree Kelvin to the 1000 degree Kelvin, and the donor atoms concentration is varies. If you form Nd is a donor concentration 10 raised to 14 per centimeter cube, or if you go for 10 raised to 19 centimeter cube, then it is showing 10 raised to minus, that is a lightly doped semiconductors. Then lattice scattering becomes important, and mobility decreases as the temperature is increases. And if you see from like approximately temperature 175 Kelvin to 550 or 600 Kelvin, the mobility is goes on decreasing. For heavily doped, same if you see, um, so if you go to the 10 raised to 10 raised to 19 per centimeter cube, that is heavily doped, then impurity scattering is the most prominent at a low temperature. If you say temperature less than 200, then here mobility increases as the temperature increases, as shown in figure. And from this we can conclude that the temperature is the one factor which plays a very vital role, and the mobility decreases with increasing impurity concentration because the enhanced impurity of scattering. Then from this we can also conclude that mobility reaches a maximum value at low impurity concentration. Uh, this correspond to lattice scattering limitation. Like low impurity concentration is like a 10 to 14 per centimeter cube. But when this electron which is moving inside the semiconductor, the electron and hole mobility decreases with increasing impurity concentration, and eventually approach a minimum value at a high concentration when we add impurities in that. And the mobility of electron is greater than that of holes, because the electrons which is having lesser effective mass as compared to the holes, and this greater electron mobility is mainly due to the smaller effective mass here. See here in this figure also, mobilities of mobility and diffusivity. Actually diffusivity d of n is nothing but the coefficient of diffusion. That part will go details in diffusion process. Here I am showing only mobilities of two material. If you see in first material is a silicon and second material gallium arsenide, which is a function of impurity concentration. Means how the mobility will be changed. Mobility will change according to the your impurity concentration. You take example here, you see from 10 to 14 up to 10 to 10 to 18 per centimeter cube. Then the value of his mobility as as your impurity concentration goes on increasing, the mobility value is goes on decreasing, which we explained before. Then here we'll go for the next phenomenon, that is called as a resistivity. And this resistivity, we know that in material we have a resistance to the flow of your charge carriers, and from that we when we apply the electric field to semiconductor, then each electron will experience a force, and that force is nothing but F is equal to minus kV. And from this, if you see in figure that is n type semiconductor material, and without field, and when we apply the field, then here the we have the conduction band energy EC, which corresponding to the potential energy of an electron, which is a rest energy. When we apply the field, then here the band gap, if you see, like we already gone through the EC, A of EI, that is which is reference level, which is the Fermi level. Then we can write here equation F is equal to minus QE minus gradient of electron potential energy, and that minus F is equal to, which is here minus DEC by DX, means the change of your potential energy with respect to the distance. That's why it is a potential energy gradient is there. And if you rearrange the term, you can write E is equal to 1 upon Q DEC dx, and this right in terms of conduction band we can write in the terms of reference energy level EI. So that your equation is become 1 upon Q dE by dx. So this factor, then one more factor we are adding here, electrostatic potential energy, whose negative gradient equal to the electric field, means E is equal to minus d psi by dx, and we can write in terms of psi the reference level and a charge. This relation between the electrostatic potential psi and potential energy ei, just before equation we are showing. For this, if you have potential energy here shown there, decrease linearly with the distance. That's why there is a negative sign is there, and the electric field is constant in negative x direction. Its magnitude equals the applied voltage divided by the sample length, and from that we can easily calculate the kinetic energy corresponding to the distance from the band edge EC. But when an electron undergoes a collision, it loses some of or all of its kinetic energy. And because when collision is taking place, that is energy transfer, and that is a electron which is moving, when it is moving inside the sample of semiconductor, we lose energy when it interact or when it collision with the lattice atoms or even impurity atoms and drop towards its a thermal equilibrium position. Then it's showing the transfer of this carrier under the influence of electric field produces a current. During this, when we apply the electric field, and these charge carriers, that transfer of these carriers under the influence of this electric field produce a current, and that current is called as a drift current, and which is very very important, because in next slide we will see how when we apply the field to the semiconductor material with the cross sectional area A, length L, with carrier concentration N, that is electrons per centimeter cube, and then applying electric field, then we can write this equation in terms of current density equation. Then current density we know in general form as J is equal to I by A. Here we Jn represent current density for electrons, and In is a current due to the electrons divided by area. This equation you can write Q with charge, and is the due to the electrons, mu1 is the mobility of electrons, E is applied field. Then just see this figure. The current is flowing across the area A, that is In is the electric current, that is current due to the electrons, and this similarly we return equation for the electrons. We can similarly write the equation for the holes, and Jp is nothing but the current density for holes is equal to Qp. Q is a charge, P is due to the holes, mu P is the mobility of holes, and is applied field. Then we can add both terms, that is current density due to the electrons and current density due to the holes. Then J is equal to, because this is like intrinsic semiconductor, both are carriers, electrons and hole as well as both are equal carriers, Jn plus Jp, and that you are getting this equation. And then conductivity we can write in this in terms of a current density, sigma is equal to Q n mu1 plus P mu v, and this electron hole contribution to conductivity are simply addition of both. And by using conductivity we can write resistivity. Reciprocal of conductivity is nothing but the resistivity, just formula is showing here. Then we have, but this is the case of intrinsic semiconductor, but extrinsic semiconductor case only one of the components is important. If we have n-type semiconductor, then majority charge carrier are the electrons and minority charge carriers are the holes. That's why resistivity is equal to 1 upon mu n q n into mu n. Mu n is the mobility due to electrons, and in p-type semiconductor, then resistivity p-type semiconductor, majority charge carriers are the holes and minority charge carriers are the electron. That's why we return rho is equal to 1 upon Qp into mu p. Then see this equation here, how resistivity is a function of impurity concentration. Before we study how the mobility is a function of temperature, or how or mobility is a function of how mobility is not only the function of temperature, how the mobility is a function of, or how it changes with impurity concentration. Here is showing how resistivity also changing with the temperature. It's for two material we have taken silicon and that is gallium arsenide. If you have dopant impurities like phosphorus, arsenic in silicon, or boron, aluminium in silicon, then we have the carrier concentration is equal to the impurity concentration. And this curve here showing impurity concentration of semiconductor if the resistivity value is known, and then how it is resistivity will change according to the impurity concentration. Then we'll go for the Hall effect. You well studied of Hall effect, but you know that a Hall effect, which is very important to determine the sign of charge carriers, and from you can determine the type of semiconductor and many more things we can study in Hall effect. Just I'm going to the few terms here. Here we are basically this equation we are obtaining for the p-type semiconductor. Consider here p-type semiconductor. Then we apply the electric field which is along the x-axis, magnetic field which is along the z-axis. Then we have two force, that is we have F is equal to Q, that is magnetic force F is equal to QV into B, where Q is a charge, V is velocity, V is a magnetic field. Then here we have the upward dielectric current causes accumulation of holes at the top of the sample, which is shown in the figure. And then here, since there is a no net current flow along the y direction, which is at the steady state, then we have two force which is balanced here, that is F is equal to QE, electric field force, F is equal to QE, and magnetic field force, that is QVP. And then we can write this balance forces QEY, electric field which is along the y-axis, QVX, V is velocity along x-axis which is charge is moving, VZ which is magnetic field which is along the z direction. And so that to rearrange the term, we can write EY is equal to VX BZ, and that we are showing all this thing which is in the figure. And then we can write here, or we can obtain this electric field which is in term is known as the, or we know as the Hall effect. And from this electric field equation we can get also Hall field. Then VH is a Hall coefficient, EY is electric field in, actually W is the thickness of your specimen or thickness of the semiconductor material which we have taken, and VH is called as the Hall voltage. Then we can write in terms of electric, this is just all equation you've gone through your solid state physics at your graduation. Then EY is equal to, we are writing RH JP of BZ. RH is the Hall coefficient, JP is the current density due to the holes, because we are taking the sample material as a p-type semiconductor material. Then we can write RH is equal to QP, means Hall coefficient is a reciprocal of or directly proportional to 1 upon of P, concentration of your holes, or Q is the charge, P is the charge carriers, that is holes. RH is equal to minus 1 upon Q, and Q is minus, this sign is due to electrons have a negative charge, and this Hall field is proportional to the product of current density and magnetic field given already. Then here, as similar expression, whatever we written for the here RH 1 upon QP, similarly we can write for the N type, RH is equal to minus 1 upon Qn. And then here we can write in terms of Hall voltage for known current and magnetic field, that is a P is a whole concentration, charge carriers are the whole carriers are there. Then we can write 1 upon Q of RH. Then RH value we have, then just the put equation, then finally you are getting equation IBZWQVH by A. And from this, thus the carrier concentration of concentration and carrier type can be obtained directly from the Hall measurement. Means Hall effect is very important to determine the charge carrier sign. From that we can determine which carrier type is there, N type is a, P type is there. We can also determine the unknown magnetic field. Then we can determine Hall voltage, we can determine Hall coefficient, number of things we can do by using Hall effect. Then diffusion process, as like you studied in material science, when atoms or molecules we move from, no doubt that is external factor when I apply, move from higher concentration to the region of lower concentration. Here also we have carriers, our holes or electrons, we can also move from a region of high concentration to the low concentration. And in terms of charge carriers means currents, we have the current, and then that current is called as a diffusion current. And to get here, understand here diffusion process shown in a figure, electron concentration, or we may call it electron concentration, or the density of electron, number of electrons per unit volume, versus distance L, which we take a distance minus L to plus L, that is the mean free path, the direction of electron current flows here showing, that is a current and electron, that is which is oppositely signed here. And consider number of electron considering plane at x is equal to 0, and then per unit time and per unit area, then we are the electron have random thermal motion at that time, and the thermal velocity Vth, then mean free path on mean free path length L is equal to Vth into tau of C. Vth is nothing but your the thermal velocity, and from that we can write like in terms of we are writing in terms of forces, like is in a fixed law also it is shown like F1 and F2 forces. Here also we see the average rate of electrons flow unit per year F1 from electron crossing S is equal to 0, means between when it is a flow between minus L to the plus L, that is charge carriers moving, then we can write in terms of equation x is equal to 0, that is when x is equal to L crossing at the right, then we can write this equation, and from that we are getting expression in terms of F1 F2, the right equation in terms of electron density and in terms of mean free time, then we are getting both value F1 into F2, and from that we have a net force F is equal to F1 minus F2 we can write, and over the minus L to the plus L we can write, and F is equal to minus dn by dx here, and then F dn is nothing but the diffusion coefficient for electron, or is also called as a diffusivity, and this diffusivity again we can write in terms of current density Jn is equal to q dn, because Jn is equal to minus q f value you already have, q dn by dx. Dn is by dx is nothing but here, that is electron density gradient, mean how that is a carriers change with a distance, and then diffusion current results from here random thermal motion of carriers in concentration gradient, we say concentration gradient like we are showing in material science dc by dx, but here is the concentration of your carriers, that is holes or electrons. Here we are electrons we are writing for this, then current is positive and flows in direction opposite to the of electrons is shown in the above figure here, then we are getting equation Jn is equal to q dn by x. Similar expression we can also write for the your holes also, but before that we see that is a whole Einstein relation, which is in terms of your mobility, in terms of a diffusion coefficient, and same we are using a theorem of equipartition theorem, which is for the one dimension case, that's why we are writing 1 half mv square is 1 by 2 of kt. Then we can write in terms of dn is equal to Vth, dn is the diffusion coefficient, Vth is thermal velocity into mean free path, and just the rearrange the term we are getting equation dn is equal to kt by q into mu n, and this relation called as the Einstein relation. This relation we are getting in terms of, because in terms of two important parameters, that is one is a coefficient of diffusion and second one is the mobility, and then here Einstein relation also applies between dp and mu p equation we can write, and values of diffusivity as shown in a figure. If you see the mobilities and mobility already, this figure already I shown before when we had took about the mobility part, then now I am showing again here for diffusivity. See here how does the diffusivity change when or as the function of impurity, which is we have taken at a room temperature, and as like your mobility, the diffusivity also changes in silicon and gallium arsenide material. Then we are going for the current density equation. Just we already written current density equation q mu n n e. Now we are adding here the term, that is both current term, the drift current and the diffusion current, that is Jn is equal to Qn mu n e plus Q dn by dx, which is for the current density for the electrons, and another which is the Jp, that is that equation. That equation is nothing but the current density for the hole due to the drift current and the diffusion current, and then total current we are getting J conduction is equal to Jn plus Jp, and that equation, these three equation we called as a current density equation, and which is very significant, or which is very playing a very vital role to determining the device operation under the low electric field in case of a semiconductor material. Then we'll go for a few numericals. For example, first one, a sample of silicon is doped with 10 to 16 phosphorus atom per centimeter cube. Find the Hall voltage in the sample with thickness is 500 micrometer. Then area is at 2.5 10 to minus 3 centimeter square. Current is 1 milliampere. Magnetic field is 10 to minus 4 Weber per centimeter square. Then just we use the above equation. Already we gone through this equation. Hall coefficient is RH is equal to minus 1 upon Qn. You are getting the Hall coefficient value. After calculation, you solve this numericals in your notebook. Check with answers. Then Hall coefficient RH is equal to minus 625 centimeter cube per coulomb. Then we can also determine the Hall voltage by using the formula we just gone through in a Hall effect. Just put the value and do the calculation. But the convert term before you use, because thickness is given which is in micrometer, you have to convert into centimeter, because other quantities area which is in the your centimeter. All units should be in one CGS system or SI system, but generally we prefer here CGS system. Then you are getting finally, after doing calculation, number of steps following carefully. Solve in your notebook. VH is equal to minus 1.25 millivolt. Another example, calculate the Hall coefficient of sodium based on the free electron model. Sodium has a BC structure and the side of Q is a 4.2 angstrom. Value is given, charge is given. Then we can calculate the number of electrons per unit value, which is for the BC structure. Then you are getting value N, and by using that, just you can get the value of Hall coefficient. Just another example, if you have N-type semiconductor, germanium has donor concentration density 10 to 15 per centimeter cube. The data is given, Bz is equal to 0.5 Weber per meter square. Then we have to determine what will be the Hall voltage if the specimen is a 4 millimeter thick. Then just write the given quantity, but the convert the unit, it should be on single system. We are just following here CGS system. Then write Hall voltage is equal to this, write the equation and put the value here, and then you are getting, go step by step, solve in notebook. Then VH is equal to, you are getting the final value. Then second one, sample is of silicon is doped with 10 to 17 phosphorus atoms, means you have N-type semiconductor, and that is charge, majority charge carriers are the electrons. Then we have to calculate the resistivity, and also we have to calculate the Hall voltage. Then what is the given value? Value is given, mobility is given here, then donor concentration is given. Then just write the what the value is given. Then conductivity you can write, put the value, and you are getting the conductivity value is a 9.6 ohm centimeter. You can check calculations. Resistivity rho is equal to 1 upon conductivity. Then you are getting resistive value 0.104 ohm centimeter. Hall coefficient you can write RH is equal to minus 1 upon E. Then you are getting this value, and finally you are getting the value of Hall voltage, that is VH is equal to 12.5 microvolt. Then we have to go for another example. Minority carriers or holes are injected in homogeneous N-type semiconductor. Sample at one point, an electric field 50 volt per cent is applied across the sample. Minority carriers distance is 1 centimeter 100 microsecond. Then we have to find the drift velocity and diffusivity of minority carriers. That is n-type semiconductor. We know that is minority charge carriers are the holes. Then we can calculate the velocity, that is a drift velocity. This is 1 centimeter, that is given distance only, distance upon time. Convert it, then we are getting velocity tends to 4 centimeter per second. If you know the drift velocity, we can easily, because applied field is given, then we can easily calculate the mobility which is for the holes, and that is nothing but 200 centimeters square whole second. And if you know the mobility for holes, you can easily calculate the diffusion coefficient, or also called the diffusivity, and that is nothing but dp is equal to 5.18 centimeters square per second. Just solve in the notebook. Next numerical. Assume that the n-type semiconductor at room temperature, electron concentrates linearly with 1 tends to 18 to 7 tends to 17 per centimeter to over distance of 0.1 centimeter. Calculate the diffusion current density if the electron diffusion coefficient is given value dn is equal to 22.5 centimeter square per second. We know this equation. We already gone through the in current density, diffusion current density. This equation, J is equal to q dn by dx. The difference in the electronic concentration. Do the calculation. Then finally you are getting Jn is equal to 10.8 ampere per centimeter square. Then we will solve mole numericals. A sample is silicon is doped to 10 to 16 phosphorus atom per centimeter. Find the Hall voltage. The given term is there. Go the number of steps, and then you are getting the finally Hall voltage. The next numerical, find the resistivity in extrinsic semiconductor at 300K. Mu1 is given, that is the mobility of electron and mobility of hole is given. Intrinsic carrier concentration is given 1.5 times to 10 per centimeter cube. Then we can use a formula, because here is the pure semiconductor. That's why we are using 1 upon q ni mu n plus mu p. If you have n-type or p-type semiconductor, then your formula is only 1 upon q in terms of mu1 or in terms of mu p. Put just the value of what is given. Then you are getting the resistivity is a 2.27 10 to 5 ohm centimeter. Then we have another example of Hall effect. Just we are already gone through the formula. You have to put the just value and solve it. Then next is your calculate the mean free time of an electron having mobility is 1000 centimeters square per whole second at 300K. Calculate the mean free path. Given is your effective mass of electron is given m0, which is the mass of electron. Put just value, rearrange the term. Then we know the equation mu is equal to q of tau of c mn. Then we have to calculate the mean free time. Tau of c is equal to mn mu n q, and you are getting the mean free time by after calculation 0.148 picosecond. And also we can calculate the mean free path. Sometimes in some book mean free path also shown by symbol lambda. Here we are showing in terms of small l. L is equal to v tau of c. Just put all the values. You are getting mean free path or mean free path length. L is equal to 14.8 nanometer. Just we are getting the more example here of minority charge carriers holes. Similar example already we solved. Just go the step by step and solve it carefully. Convert your whatever the given quantity in the only one system. Generally we are prefer CGS system, but the convert, if you have given centimeter in terms of meter or another any quantity in both system, then you have to convert. Then here we are calculate the diffusion minority of carriers dp, that is the minority of holes, and just go step by step. Then we are getting answer dp is equal to 5.17 centimeter whole second. Just another few example. Just we are already gone through it. You have to solve in notebook. Go step by step. You can easily, you are getting, solve it carefully and find the room temperature resistivity n-type semiconductor tends to 16 phosphorus atom per centimeter cube. Then this is n-type semiconductor. Then we can resistivity. We know the formula. We are just to put the value, do the calculation carefully. Then finally we are getting the resistivity value. These are the more examples which is based on that. We have to already we've gone through the Einstein relation, and from that we can put the value just. Then find the diffusion coefficient of electrons and holes. A silicon sample crystal is given parameter is there. Then put the value of it and solve it carefully. Okay, we saw all the numerical which is based on this. I used following this reference book for that, and especially I use a book, and for the some numericals I use also SOP like problems and solution. Then with this carrier transport phenomenon, then next lecture we'll see important topic is the excess carriers in the semiconductor, and how this excess carrier, if you injected or introduced in your intrinsic or an excess semiconductor, then how the carrier density or how the carrier density is changing there. Or we have to say also the details about the generation recombination phenomena, which includes your photoluminescence and photoluminescence and other we have to see a phenomenon, and also we'll see a number of numericals which is based on that. And then finally also we see next lecture, that is how the device equation or semiconductor device operation in terms of which equation especially we use. Already we've gone through current density equation, other equation, how we use for the device operation for the semiconductor material. Thank you.